Again, Omniperf is not part of ROCm. You have to install it yourself. Built on Rock Profiler, like it uses some Rock Profiler. And it has a lot of analysis. It integrates speed of light, roofline, memory chart, baseline comparison, local data shared memory, vector L1 data cache, L2 cache, everything I would say. It supports MI200 and MI100. Roofline is only for MI200. And it can visualize through Grafana GUI standalone command line. So as I said, Omnitrace is about kernel. So it needs to run with one API process, not more, not two, not three, only one. It will use one of the GCDs. And the Rock Profiler will run many times. It depends on what you're doing to gather the counters and to do micro benchmarking to do the empirical roofline of the GPU that you use. So the roofline with the top results will be calculated and not theoretical. And then there is the CSV suite that then goes, or you go to database to import to use the Grafana, that we will not talk about the Grafana here, or go to CLI and use even text or web-based, I would say, or web-based GUI. Omniperf supports many features that we'll discuss some of them, but not all of them. It's too many and not always easy to understand. So Omniperf is an integrated performance analyzer for AMD GPUs built on Rock Profiler. If you just run it without any argument, it will run around to 17 times the application, gathering different counters for its execution and tries at the end to combine them to understand what's going on. So 70 times means that if an application needs 30 minutes to run, it is going to run for more than 8 hours, right? So you need to be careful what you give as input to Omniperf. Now, if you want to do only roofline analysis, it can run 3-4 times and that's it. But you will not have the data about the other analysis, memory analysis, etc. Omniperf shows many panels of metrics based on hardware counters. We'll show a few here. Typical Omniperf workflow is a profile, analyze with CLI, or visualize with standalone GUI. Or profile and import to database. I will skip the database because I don't do Grafana here so much. Omniperf targets MI100 200 and it requires to use one API process. Again, for any issues, you can use here to clear issues, what happened, what's wrong, etc. Installation. Basically, I will skip it because you can read it. You have the slides. But as I want to show you, it's basic, no root access, nothing. You can install any version you want, and just it works. Okay. And also full documentation is here. There's also some documentation about this. Now, profile. Target application is launched using AMD Rock Profiler. Kernels dispatches IP blocks. Now, what's IP block is basically, let's say, a collection of counters that are related between them. We analyze profile data is loaded to Omniperf CLI, immediate access to metrics, and lightweight standalone GUI. So you have or TXT or a GUI. You can do Grafana. I have done sometimes Grafana, but I will not talk a lot about it. I will talk about maybe with experience I had with some big applications about Grafana. And now, how you run Omniperf, what I want to do, profile. How I want to call my experiment, dash n, and how you want to call your experiment. This is a word that you define. Any other options, any roofline options if you want, dash, binary, and argument. So the dash is the same like Omnitrace, okay? Now, I finish my execution. How to analyze my data? Omniperf analyze -p where path to workloads, workload name is the name of this one, MI200. So when I define something here, let's find, I don't know, define it Friday, I'll have a workload / Friday / MI200. Okay, so this way you can go here, Omniperf analyze -p and this will produce a lot of output, so better redirect to a TXT file. If you want a standalone GUI, then I would say copy the data, the workloads directory to your laptop or desktop, and do this Omniperf analyze P, the same command, but that's the GUI. And this will tell you, go to web browser and to this link and load it, and you will see your data. Okay, it's loading something like a local simple server. And this is about databases, the interaction and connection with the Grafana. And always you can see the help Omniperf profile help. Now, for example, you can test an example. We get an example. This is vector copy example. You can compile it, and you can run it like that. Of course, it just run here. Omniperf profile. I just name it vcopy all. Does and how it runs. Okay, and it will run many iterations, and it will create the data. A new directory will be created called workloads vcopy all. Now, Omniperf workflows. Okay, do you have access to Grafana server? Omniperf import, load Grafana, visualize, analyze. If you want only CLI, Omniperf analyze and do CLI analysis on the terminal. If I want the standalone GUI, download data and Omniperf analyze with standalone GUI, load the mentioned web page from your web browser, visualize and analyze. If SSH forward allowed, you can use it to avoid downloading the data. So in the previous one, when the vcopy finishes, I can do analyze this and extract everything to vcopy analyze because it's a lot of information. And I will see top 10 kernels. This has only one kernel. How many times it's called, the duration, and the speed of flight is here. So how many flops I have? Vcopy is vector copy, is only memory, so I have 0 flops, which means I will not see a roof line, and I will explain that. Here says active compute units, 52 from 110. What does it mean? The GCD in amount of 50x has 110 compute units. If you use 58 of them, and you don't do it on purpose for a specific reason, then you don't expect that you utilize all the GPU. This is what it tells you here, for example, right? And here's telling you about how much you utilize VLU, SLU, etc., MFM operations, and it's not a lot, right? This is like 52%, 38.7%. This is percent of peak, okay? And here's the peak values. Wavefront large statistics is about the grid size, the workgroup size, total wavefronts, and the registers, etc. So you get a lot of information. This is just 3 tables from around, I would say, you can have 800 lines of various data. So it's a lot. Now, I'll go back a bit. Do you see here some numbers? 0, 7.1, 7.12. You can do analysis and says, I want to analyze and give me B0, only the top statistics, top kernels. The result is only this. If I say I want the total, the wavefront, total wavefronts B710, 712, because 712 is total wavefronts, I will take always the top kernels plus the wavefronts. This is about, because you can have a lot of data and it takes a lot of time to analyze, to extract specific part. And of course you can do Omniperf analyze.h and that's h and see the help, all the options that you can use for analysis, normalization, etc. The data are normalized per wavefront, all the data. You can do das n and says per kernel to normalize per kernel, for example, etc. easy things you can check. Are all the compute units being used? If not, more parallelism is required. Are all the vector registers being split? Then smaller workgroup sizes. Is a code integer limited? Try reducing the integer operations usually in the index calculation. So there are a few things you can check, let's say, fast. And in this example here, I do the view copy with the GUI, and when I do GUI, it says open web page, it gives me an IP or localhost 8050, and this is screenshots from the web page, and if I can zoom like here, you can see 58 webframes from 110, the registers, the request, read the request, write request, LTS 1% utilization only, latency is 47 cycles, vector L1 cache, hit rate 60, I think, yeah, 69%, and other information, right? And you can see the exchange and the fabric to go to other GPU, to go to HBM, etc. So you can see a lot of information about to understand more about the memory. And similar, here is the speed of light. We saw that it was 0 flops, etc. Here's the instruction mix, okay, and again, here branching SLU, VLU. I have here integer 32. Here is okay, still yeah, it's still okay. Basically, you have a lot of basically integers. And if you want to import it to Grafana, Omniperf database import connection options to Grafana. Grafana is nice because you have all your data there. You can do 100 experiments and have them there. If, of course, don't crash Grafana. So that's another story. And with Grafana, you can have more fancy colors, options, menus. You can compare to executions and other stuff. So there are some, let's say, benefits. So key insights from Omniperf Analyzer. Yeah, when accessing performance difference between two workloads, it's good to know the differences between underlying systems. So this is from Grafana, and you can see, for example, see some different numbers, raw conversion 1.3, 5 to 0. So because this keeps track of what system you run it also, for example, right? So that's interesting to have it. Initial assessment with kernel statistics, instruction data flow, speed of light. So again, as I showed you before, memory chart and active compute. Now the red doesn't mean always bad, right? Active compute use is 100, so that's okay. Or utilization, that can be okay, for example, right? It's not doesn't mean bad, but it's usualized like that. Now, roofline is the first step characterization of workload performance. And what you can see, I will explain it later. So you have this stuff. Arithmetic intensity is down, which flops per byte. And this is the gigaflop performance. If I'm close to here, I'm getting compute bound. If I'm close to here, I'm memory bound, okay? If I'm close to here, it means that theoretically I can improve the performance. Okay, so it's kind of easy to understand what's wrong. And this is what is a roofline. So this is quite introductory. So we have this plot, okay? Attainable flops per second, which means achievable, okay? Yeah, I suppose you know what the flop, number of floating operations performed per second. Add is one flop, multiplication one flop, FMA two flop, and we have this example, right? Xi equal yi plus c. Have flops one, this one, okay? And the bytes is one read and one write. Okay, which is in this case is 4 plus 4 equal 8. So arithmetic intensity is flops per byte, so it's 1 divided by 8 in this case. This is log-log plot in order to be able to plot and without having issues. And basically, the compute is a peak flops, and memory is memory bound HBM is the arithmetic intensity time peak of gigabyte per second, but we have also the LDS, L1, L2. Okay, so these are empirically numbers that will show you, with not theoretical. Now, okay, once here where AI, this here is a machine balance, okay, but typically machine balance is 5 to 10 flops per byte, but in M250X the machine balance is 16 flops per byte. We need around 120 flops per W to exploit compute capability. This is just for information, it's not something like to remember. You cannot be above this one. I mean, you can with metrics course, but this is a different story. And also you can be above HBM by using LDS, L1, but I'm talking about related to HBM and related to the normal computation. You are compute bound when you are close here. There's no number to say how much close here to be, and it's also log. But it's about your feeling and your experience, how close you are, and bandwidth bound. So usually when you're here and here, you cannot do something to improve it significantly, except if you know something algorithmically. And here's a poor performance that has potential to improve. Okay. Now, final results is a single roof line plot presenting the peak attainable performance on a given device based on arithmetic intensity. Now, a nice example is this: we run a number of kernels and measure flops per second, right? So this is the highest flops per second, and this is the lowest. Okay, kernel A to H. And the question is, which one is good performance? We sort the kernels by arithmetic intensity. So we take the arithmetic intensity and we sort them, okay, like that. And then we compare performance relative to hardware capabilities. And then you start seeing like that. Kernels near the roofline are making good use of computational resources, right? Kernels can have low performance, but make good use of bandwidth, for example, right? Like the red. Or increase arithmetic intensity when bandwidth is limited, reducing data movement increases arithmetic intensity. Kernels not near the roofline could have potentially the option to improve performance. So that was about the roofline. Now, I don't know how heavy is this light. This is the one TCD, right? One TCD is the one part of the, if you remember, the MI250X has two of them. And this is the compute units, okay? We have 110 of them. Each of them has local data shared memory, okay? Has 4 SIMD that execute the wavefronts, scalar unit, okay? And scalar registers, vector L1 data cache. This one is the, let's say, this LDS, and then this cache memory. And when it goes out from L1 cache, it goes to L2, and then it can go around to other GPUs, etc., or to memory controller, HBM. So this is about to see the layer stack to understand more a bit some things. So here you see the peak VLU gigaflow per second. But here, this is if you do matrix operations and use a matrix course, you can even double the performance compared to here, okay? So this is something else. And this is HBM, okay, L2, L1, and LDS. LDS also has a quite high bandwidth. And the workload performance here, okay, gigaflow per second basically it's AI arithmetic intensity, gigahertz per second. And I don't want to, yeah, okay, I mean, so we run some macro benchmarks to measure the actual peak bandwidth, peak compute actually happening on the GPU that you're using with some HPC benchmarks, matrix multiplication, pointer chasing, streaming copy, etc. to have all the data for the peak bandwidth. And we have some rules like the weight flops is one for these operations. For transcendental is like that. Is also one. Now profiling requires 3 applications replace, and there are plenty of counters that it's not our purpose to explain here, just to show you that when we use the flops, for basically on the wave fronts, on everything, FP64, 32, 16, and more machine learning stuff, etc. I don't describe the formula, we compute the arithmetic intensity based on hardware counters, and then here basically you can take the counters and do it yourself through Rockproof to calculate the roof line, because you can take the hardware counters and do 1, 2, 3, 4 different, 5 different executions, and you can calculate it, the roof line yourself. So now, one moment, because I'm thinking here is about. I want to skip some things because of lack of time. Here's a Grafana visualization, so it's something similar as before, but I want to skip because I have some, they were from statistics, we saw them already before, because I have one example. Yes, if you want to do roofline only, the application will run 3-4 times. Then you can do profile, that's and your name you want, and that's roof only, okay, and your application. This does roofline only, and you can see then your kernel where it is, for arithmetic intensity L1, L2, and HBM, okay, and you can see what happens. If you want to see the name of the kernel, you can activate the kernel names here, and you will take a second PDF that basically you have the kernel names. Here's the web page. When we load the standalone GUI, I can select the kernel and visualize. This is for Cocos, that how it was working really good to visualize some stuff. I will not. I will skip some stuff. Now, yes, what if Grafana and Web GUI crashes when loading performance data? A real case. So I had a real case with 6.7 million calls to kernels. I was creating a ton of data, 8 gigabyte, 9 gigabyte. When I was loading to Grafana was crashing. The standalone GUI was not crashing, but never loading basically. So in that case, because we do analyze the top 10 kernels, you can use the option -k to run per kernel. So you do 10 runs, 1 per kernel, and you can visualize independent each of the kernels. Okay, not all together. This way, you can decrease the data and you can visualize what you want. This is mainly the lesson that we took from some big cases. And also you can run them in parallel to not waste time, but of course the roofline can be different, okay? And this is something I want to show you. Double precision A times X plus Y with a loop in the kernel. So, simple code, okay, it's a really simple code, DAGP. Okay, Y equal A times X plus Y in a loop 20 times. Defined like that, okay? A big number, okay, I don't care for the rest, the rest are simple things. Okay, this one. I do the kernel, the roofline, and I see that my kernel is not good, can be improved, it's not memory bound, performance is almost 330 gigaflops here, I think. If I'm correct, yeah, I think it's correct. And what we're doing here, what happens? I'll go back again. Because we have here pointers, the compiler does not know if the pointers can sort to the memory to the same memory address. Okay, so what we're doing, sorry, and also here, when we do the kernel execution time, we see that it runs. This is like 2 million nanoseconds, 2 seconds, I think, and the total request, write request, read request, and the total, that is a lot. It's more than 1,000 write requests for this, while this would fit in the register, etc. Should not have so many requests. So these numbers, from L1 data cache access, that's why I showed you before the architecture, is quite significant a lot. While you see the cache utilization quite high, etc., this is suspicious. And because, as I said, the compiler thinks that the X and Y can be in the same, can point to the same memory address, it's much more careful. And what we do, we add the restrict options here, which we say to the compiler, don't worry, they will not be the same. So don't worry, try to do any optimization you can. Okay? So by doing this, and then plotting the roofline, we have this. So the performance, almost 2 teraflops. So from this, 330 gigaflops, we go to 2 teraflops only from these small chains. And if we plot now, the time is 6.2 times faster. And guess what? The request per wave, 64 write, because of course one wave has 64 threads, right? So it will be 64 write operations here, because we write just once, right? And we read twice. Okay, and we read twice. So the numbers now is correct. And we got 6.2 times faster. So what I want to show you with this is that you need to be suspicious your kernel, what it does, what I should see from the kernel. So the numbers by themselves sometimes don't say a lot, because here you see the number is 16.3. There are 16 more tables before this one. There are a lot of data that the before data maybe didn't help so much, like this one, to see that, oh, I have a lot of write, read, total requests here, so something is wrong, okay? Of course, if you have a kernel of 500 lines, it's not so easy to see that. So this is more easy case to see that, okay? So that was, I want to show you an example that seeing some numbers and try to understand the correlation with your code, how to help you improve the performance. So I know that this was quite, I was not planning to show you all the slides either way. The Omniperf is a tool that it gives you a lot of data. So you need to know quite well your kernel before you go to read the data. That's a difference, I would say, with Omnitrace. Do you have any question? Okay.